In today's topic, we'll go through an important discussion in electrical electronics engineering under the topic filters. So let's start with introduction to filters. Now, filters are used in a lot of application in electrical electronics engineering. The signal that we receive into electronics components is filled with range of frequencies, and to make sense of a received data and to interpret it into meaningful information, we need to be able to choose a selected bandwidth of frequency. Therefore, these filters would help us in achieving this objective, and we have some important choice of filters, and this will be discussed in today's session. Now, before I move on to the introduction of these filters, I'd like to revise on some important topic called impedances. So an impedance is a resistance to current flow. So the most common electronic devices are the resistor, capacitor, an inductor, and of course source. In most of the electrical electronic circuits, you will find these components, and each of them will have some resistance to current flow called impedance. So an impedance of a resistor R is designated by ZR. This is equivalent to R, as you remember. And for a capacitor C, this impedance is ZC, which equals to 1 over J omega C. And for an inductor L, its impedance is ZL, which equals J omega L. Okay, now, so we'll see how these impedances are combined in a circuit to give us some specific output. Let's look at some of these combination of impedances. Now let's start with a resistor. Assume that we have a current flow, and this is designated by I, and voltage, which is V, and we have voltage across each of the resistors, VA and VB. Let's say our objective is now to find what the value of this VB is. Alright. Now we can start with calculating the total resistance. We know that the voltage across is V, and our total can be given by the voltage divided by the current, and that should ideally be the sum of the two resistors RA and RB. Now from this it follows that we have V, which equals I times RA plus RB. We can understand that that current that flows through the whole of the circuit is constant through that branch there. It's a continuous branch, so we'll expect that current to be the same throughout RA and RB. Now if I then define that current in terms of those two variables VA and RA, I can then rewrite this in the form of VA over RA. So this will give you the same current I, and we still have that RA plus RB. Now, as we said, the objective is to find what that VB is in terms of the voltage and the resistances. So by rewriting this and solving for VA, you can see that VA equals V times RA, because this part here is a numerator, it will go as a denominator across the equal sign, or it is just dividing by RA plus RB in both sides will give you RA plus RB as a denominator. Let's call this equation 1. Okay, equation 1. Now you can see that in equation 1, if RA increases, then we would expect VA to increase, and if RA decreases, you'd expect VA to decrease, so they have direct relationship. Now if the question had been to find VB, you can therefore from this tell that VB should be given by V times RB over RA plus RB. Again, in the same way, if RB increases, VB increases, and if RB decreases, VB decreases. They have direct relationship. This is called voltage divider rule. VA gets portion of V, which is multiplied by RA over RA plus RB, and VB, voltage across RB, gets portion of V, which is multiplied by RB over RA plus RB. Let's call this equation 2. Now we will add one more example. Let's have resistor and capacitor. The impedances of this resistor and capacitor are ZR and ZC, and we know how they are given. Again, in the same way, our objective is to find what the voltage across this capacitor is. Let's call this VR. We know also what the voltage across these two start and end node are. So finding VC is the objective. So we can learn from these equations, equation 1 and equation 2. We can then say that VC equals V times like same proportion of V, which is V times. Because it's VC which is required, so we'll have the corresponding impedance at the top, so that will be ZC over ZR plus ZC. Okay, but now we know what this means. ZC is given by 1 over j omega c, so that will be 1 over j omega c over ZR is R as given here, okay, plus ZC is 1 over j omega c multiplied by V, okay. So VC equals V times, alright, 1 over j omega c over j omega c times R will be j omega cr plus 1 over the whole j omega c. Now, so because we have now similar denominators, this cancels out, okay, so we'll have V times 1 over j omega cr plus 1. Okay, so the circuit we have is this, and we can redraw this in the following form. So all we have done is just bend this wire 90 degrees at this point. So the rest, circuit wise, this is still the same circuit. Okay, that's our capacitor and our resistor. So we have V input, which is V measured from this node to the ground. So we have input V. We were interested in the voltage across the capacitor. So if you remember, our solution for VC was given as V at inputs or source voltage times 1 over j omega cr plus 1. So then I can further rewrite this in the following form. VC over V equals 1 over j omega cr plus 1. Now this helps us to study the property of this circuit. So how does this circuit respond to inputs of different frequencies? What would the output be? Right. This is called also transfer function H omega. Now what we are interested in is to find the relationship between this frequency, because once we fixed our capacitor and resistor, so we will be playing with this frequency. So what happens to this gain as we increase or decrease the frequency? So to study that, then let's just take two cases. Now when the frequency is very low, then our VC over V is 1 over j omega CR plus 1. But because omega is very low, that part is basically 0. So what we have is 1 over 1. Okay, 1 over 1. So which is 1. Okay, 1 over 1. Then if case 2, so if omega is very large, our VC over V, which is 1 over j omega CR plus 1. Now if omega is very large relative to 1, this is a very large number, so this reduces to 1 over j omega CR. And of course we are interested in its magnitude, okay, and that will be 1 squared over j omega CR squared in the squares, okay, so that will be 1 over omega CR. Alright, and now if we can plot these two cases, alright, so that is omega and this is our VC over VI, okay. So from case 1 we see that for very low frequency the gain is 1, so let's say that this is where 1 is, okay. Let's say that that is 1. The horizontal axis is our frequency axis, so that will be low frequency, high frequency areas, okay. For low frequency we have our gain to be 1, and for high frequencies, this will be a function of omega, which is as omega increases, if we have high omega, the total value will go down, okay. So for high it will be very low values. So we can connect this in such a way, okay. Alright, so this is what it looks like. For high frequency we have low gain, and for low frequency we have high gain. If we redraw this circuit lets through low frequency signals but attenuates high frequency signals. Mind you that VC over V when the frequency is low is 1, so it means that VC is actually the voltage V. This means VC is equivalent to voltage V. Now for low frequency our capacitor is acting as an open circuit, but at high frequencies we'll be looking at this output, alright. Then at high frequencies 1 over omega CR will be very low. Now it means that for high frequency our capacitor is acting as a short circuit, so the voltage measured here will be very, very small. So for omega high, so this is as if we have V over VC over V was 0, okay. So this tells you that our VC is V times 0, okay. Now if you have a low frequency signal, the low frequency signal will pass through, okay, while it is amplitude unchanged, alright, its amplitude will remain unchanged. The high frequency signal at output will be attenuated, as you see, it will be taken to almost 0. So ideally you will not get the high frequency signal, but that's not going to happen. What happens is that you will have that high frequency signal, but it is highly attenuated, okay. Let's say this is the amplitude of the source, but the amplitude of your output amplitude will be very much attenuated and you will not detect it at the output, okay. Such a circuit, alright, is called a low pass filter. So as a result we have a low pass filter, or called LPF, as it only passes low frequency signals, okay.
I think these videos are brilliant and I'm sure you will like them too. Please like, comment, and subscribe. And don't forget to click the notification bell.